Now, when you place a conductor in an electric field, remember an electric field is an influence on charged particles. Something is creating an electric field, something external. We won't worry about what is creating it. But whatever is creating it is trying to push charged particles around. It influences the space around it, causing charged particles to experience an electrostatic force. So when you place a conductor in an electric field, you're placing a conductor in a region of space where there is an influence on the charged particles in that conductor. Now, in an insulator, the charged particles are tightly bound to the material in that insulator, and those charged particles don't move around. Even though the electric field is trying to push them about, they do not move, unless the electric field is incredibly powerful, and we'll get to that later. But in a conductor, the definition of a conductor is that the charges are free or fairly free to move about inside that material. Like in iron or copper and aluminum, these are materials where the electrons are very loosely bound, so they're free to move about basically inside that metal. Think of them as a soup of free electrons that can easily move about inside that conductor. When you place a conductor in an electric field, it does influence those free electrons. And those free electrons do move in response to the electric field. They rearrange themselves inside the conductor, so the electric field inside the conductor becomes zero. And the way to think about it kind of makes sense, right? If there's an electric field in a conductor, the charges will move. The charges will move until there's no more electric field inside the conductor, right? No more electric field means no more electric force, which means no more moving charges. So, if you add unbalanced charge to a conductor, for example, let's say you have a metal conductor, a sphere of metal, and you add positive charge to it, right? By taking away electrons from the conductor, or by adding electrons to the conductor, you give it a negative charge. In this case, imagine we're adding positive charge. In reality, we're taking the electrons away. But if this is a conductor, when we add charge, the charge deposits itself on the surface of the conductor, and it very quickly moves to redistribute itself evenly across the surface of that spherical conductor. One way to think about it is like charges repel one another, right? They hate one another, so they move to get as far away from one another as possible. Now, this analogy doesn't work with more complicated geometries like pyramids and so on, but realize that the charges will reorient themselves until the electric field inside that conductor is zero, which means that all of the electric charge that you deposit on a conductor, all of that excess charge moves to the surface of a conductor. No charge remains inside the conductor, inside the solid conductor. All of the charge moves to the surface. Now, this has important applications in what are called Faraday cages. You might have seen examples of a Faraday cage, and I'll try to link one in the notes section so you can see it in action. A Faraday cage is a metal cage that, when you're inside, you are insulated from electrical discharge. So very high voltage arcs of electricity can hit this Faraday cage, but you are protected. Your car often acts as a Faraday cage when your car is struck by lightning. If your car is struck by lightning, you tend not to get electrocuted if you're inside your car, because the metal cage you are in, that is your car, keeps all of that excess charge deposited by the lightning bolt on the outside of the car. Most of it then bleeds off into the ground. A small amount might remain outside. So if your car is struck by lightning, one thing you don't want to do is immediately open the door and step on the ground, because you complete the circuit and you can electrocute yourself. But most of the charge actually does drain off of your car. But you are protected inside your car because of this property. So if excess charge is placed on a conductor, it moves quickly until the charge is on the surface of the conductor, arranged in such a way that the electric field is zero inside that conductor. We call this state electrostatic equilibrium. This happens very rapidly. Now note that I'm just depositing a little bit of charge and then leaving it. I'm not putting a current through this conductor. We'll talk about currents later on this semester. We're just talking about depositing some excess charge in a conductor and have that excess charge move quickly about. If I place excess charge on an insulator, this does not happen. Charge cannot freely flow in an insulator. So if I place excess charge on an insulator, that excess charge stays basically there. It does not rearrange itself to make the electric field zero. That only occurs in a conductor. And conductors then reach that state of static equilibrium.